Years ago, there were many Fridays where I was heading out to my last call for the day. I started taking some multimeter readings, and the readings make absolutely no sense to me. It's hours past the time I normally go home. Customers getting a little concerned, asking, is everything okay? And yeah, but on the inside, I'm ready to rage quit. So what we're going to talk about in today's videos are key things that I just didn't understand at the time that led to all those late, frustrating Fridays. Now, it's not the most interesting topics in the world, but the few minutes it takes to watch this video can save you all those hours of frustration. So the first thing I want to start off with is understanding how to pick proper reference points with the probes on your multimeter so that we can get an accurate reading that we can properly interpret. What you're looking at here is a diagram I made of a basic circuit, right? So we have our power source, we have our hot wire, we have some point of resistance, which could be a coil in a contactor or a relay. It could be a winding in a motor. It could even be an open switch. And then on the other side, we have our common or neutral. That brings us back to our power source. Now, when you use a multimeter to take a voltage reading, your probes have to be on both sides of this circuit that's separated by this point of resistance in order to actually get a voltage reading. And this is because a multimeter reads potential difference between 2 points. Now, potential difference is the ability for voltage to push current through the point of resistance to the other side of the circuit and back to the power source once that circuit is fully complete. So it's basically telling you the potential for energy to travel from one side of the circuit to the other. Now, this point of resistance, whatever it might be, creates that potential difference. If we were to place our probes on the same side of the circuit on either side of that point of resistance, we're going to read 0 volts, whether there's voltage there or not. And this is because there is no potential difference on a wire that's reading 24 volts, 120 volts, or 0 volts all the way through it. The readings are exactly the same all the way through, so there's never going to be a difference. The difference will always be 0. If you're using improper reference points and you're reading 0 volts when there's actually voltage there, or if you're using proper reference points and reading 0 volts because you have a problem with your power source, these are two completely different things. So understanding reference points tells you the difference of what you're actually looking at there with your multimeter and pointing you in the direction of the actual problem. Now, circuits are never really this simple. They always include some kind of control switching. They include ground wires. And so the number of reference points that we can use to get a reading will start to multiply. What also can happen is, depending on the position of these control switches, proper reference points can actually move around. So it's not so static. So let me show you what I mean by that. If you look at this diagram, you see there's an open switch, right? So our hot wire, that red line there up to one side of the switch, has voltage on it. On the other side of that switch, we don't have any voltage. And so that open switch provides a point in resistance. That air gap between those two terminals is resistance. And so now we have a potential difference of one side of the switch and the other. But once that switch closes, we no longer have a potential difference there. A closed switch is not like a coil or a winding. It doesn't provide much resistance at all. So we lose that potential difference. Now, what that means is that in order for us to get a voltage reading, we now have to move one of our probes to a different reference point so that we can again see a potential difference. And that next point is going to be on the opposite side of whatever the next point of resistance is in the circuit. Now, here's where all this talk and theory can really pay off in a real diagnostic situation. Let's go back to the closed switch. If I were to put my probe on the hot side of that switch, and then I place my probe on the other side of that switch, and let's say I'm reading 0 volts. What I'm dealing with here is a problem of not knowing whether or not I'm reading 0 volts because I have a power problem that's not delivering voltage to begin with, or if I'm reading 0 volts because I have no potential across a closed switch that's actually powered circuit. So what I have to do is I have to move my reference points around in order to verify my readings so I'm not being fooled by these things. So what I would do is I would put my probe on the hot side of that switch. I would take my other probe and select a reference point close to the power source at the common terminal of a transformer, for example, and I should be reading 24 volts there on that hot wire. regardless if that switch is open or closed. Once I can confirm I have voltage there, I now know I don't have a power problem. So if I go ahead and I move my probe to the reference point on the other side of that switch and I'm reading 0 volts, I now know I have a closed switch because that switch has no resistance to it, there is no potential difference, and so I will be reading 0 volts. If I read 24 volts, I now know I have an open switch. And so this is how I can use different reference points, verify my readings, and get actual numbers on my multimeter that make sense and tell me something. It tells me whether I have a power problem or I don't, whether I have an open switch or a closed switch, and so on. Now let's talk a little bit about the ground wire. The ground is an alternate path for power to take in the event there's, like, say, a short in a circuit. So if there is a bare wire on the hot side rubbing against the chassis of the unit and that unit was properly grounded, we would have a safe path back to our power source. And so that ground wire can be used as a reference point as well, or even the chassis itself, if it's grounded, can be used as a reference point. Now here's the problem with that. If I were to put my probe on, let's say, the hot wire and my other probe on ground and I'm reading 0 volts, once again, that does not tell me whether or not I have a power source problem, or maybe I have a problem with a circuit not being properly grounded. So that voltage reading doesn't really mean anything to me. Now, if I expect to see 120 and I do read 120 off of ground, well, then that's telling me I have a properly grounded circuit. But you always want to kind of default to common or a neutral wire to get an actual voltage reading, and then just verify by using your ground to see if you're getting the same thing. So if I went from hot to common or neutral, I read 120, and then I went from hot to ground and I read 120, well, that's telling me I have a properly grounded system. If I have 120 between hot and neutral, but like 50 volts or 60 volts between hot and ground, well, that's telling me I don't have a properly grounded circuit. Now, sometimes that might be the problem we're actually looking for. But you always have to be aware that ground is a little bit of a risk if you're not quite absolutely certain it's properly grounded. So using common or neutral is always the better option as a first choice to select as a reference point, and then you can always use ground as a verification. Now, one last thing I want to talk about is voltage drop. This one definitely threw me for a loop and had me tracing circuits down for hours the first time I ran into it. In a nutshell, what voltage drop is an unintended form of resistance in the circuit somewhere prior to the component we actually want to power and activate. So for example, if we're trying to push voltage through a corroded terminal on a switch or a control board, that little form of resistance will have the voltage trying to push current through it. And these forms of resistance can turn that energy into heat. And so what we end up with is a measurement on our multimeters that show a drop in voltage prior to our relay coil in this example. So we can see we have 24 volts coming into a closed switch, but we only have 16 volts coming out. And that 16 volts is not sufficient enough to actually activate the relay coil. So this is something you're going to run into a lot out there in the field. Now, this is another reason why I don't particularly like using ground as a reference point, because again, this is another situation where it's very difficult to tell the difference between an improperly grounded circuit or you're actually experiencing a voltage drop. So I always like to use common or a neutral as a first choice, and then you can always use ground as a verification. So in order to weed out these kinds of problems, once you confirm you have a voltage drop, basically all you want to do is you want to just kind of hopscotch backwards from that point and see where that drop is actually occurring. So in this example, let's say I put one of my probes at the relay coil, the other probe on the other side of the relay coil, and I'm only reading 16 volts. At this point, I can go backwards to the terminal on that closed switch, reference common, and see what my voltage there is. Now, if I go to the hot side of that switch and I'm reading 24, well, then I know I'm experiencing a voltage drop there between that closed switch. So in this example, we have a voltage drop of 8 volts. We got 24 volts coming in, 16 going out. The difference is 8 volts, and that's where our problem is occurring. Now, these voltage drops, they could be caused by corroded and pitted terminals. They could be corroded wires themselves. Sometimes you just have to cut them back and restrip them to fresh copper. Sometimes it's caused by loose wire nut connections. I mean, basically, you're looking at the integrity of all connections and terminals through this circuit, looking for these sorts of voltage drops.